A related question is this. Suppose we have a wire and we measure the current at two different locations. Let the current in here be I1, current in here be I2. Question is this: should these currents be the same? This is an interesting question, so I would like you to pause this video and think about this question for a minute. So think about the possibility, for example, if these are slightly different. Let's say that, for example, I1 is equal to 1.0 amperes and I2 is equal to 1.1 amperes. Is this possible? Okay, if you have thought about this, and I can give the correct answer. So the real answer is that, of course, the current that is flowing through that part of the wire is basically a property of this determined by the electrons in here, and those electrons do not know what the electrons in that part are doing. So as a result, they are not obliged to create a current that's exactly the same as the current in here, right? So if you just think about it, I mean, these two are two physical systems. So as a result, if the currents at these locations are just the properties of these physical systems, they don't have to be the same. So in principle, they can be different. However, this kind of a situation cannot continue for a long time. So in that case, you have to just imagine this kind of a, I don't know, just consider this part of the wire as some kind of a physical system. So in that case, I can define the total charge within that part of the wire. So as a result, I1 is a current that that flows into that region, and I2 is the current that flows out of that region. Since these two currents are different, that means that the total charge inside that region is changing. So we can easily write down the expression for it. So dq divided by dt, if we had only the current on the left side, in that case, this I1 would be just the amount of the increase of that charge. And if we had only this I2, in that case, of course, that would represent a decrease of the charge. So therefore, the dq over dt is just I1 minus I2. So if we just accept these numerical values, this is equal to minus 0.1 amperes. Okay. So this is actually a huge current. So suppose that in 1 second, let's say, this current difference is somehow maintained. In that case, the change in the charge in that region would be minus 0.1 coulombs. So if I assume that initially, for example, if the charge was equal to 0, in that case, the charge at the time at 1 second would be minus 0.1 coulomb. The important point in here is that this is a huge charge. Okay, if you think about it as some kind of an electronic circuit, for example, in that case, this distance is kind of small. Let's say this is like around 10 centimeters, 1 meters, 1 centimeters, and so on. So this much of charge collected in this kind of a small region actually carries with it some kind of huge forces. So you can think of it like this. I mean, imagine that part of the wire as consisting of two subparts. In that case, the charge in here would be 0.05 coulombs, and the charge in here would be 0.05 coulombs, and they will have some kind of an separation of the order of about 10 centimeters. So just imagine the amount of the force that would be acting between these two charges. So it's like we are going to use the Coulomb's law for that. But of course, we cannot exactly compute that force. What we can do is we can write down an order of magnitude expression. So K is of the order of like 10 to the 10 in SI units. Charges are both of the order of 10 to the minus 1, so their product is about 10 to the minus 2. The distance about 10 centimeters, so that's 10 to the minus 1. And that also gives you something like that. So as a result, you get a huge force, 10 to the 10 newtons. So an ordinary wire cannot stand to the tension produced by such kind of a force. So as a result, for an ordinary wire, it is not possible that there can be a charge pileup of that order of magnitude. Okay. So what we can say in here is that, yeah, the currents can be different. The currents in here can be different. But if that difference is large, that difference cannot be maintained over a long time. So 1 second is a huge time. So probably within a very short amount of time, that difference is going to be disappear. There can still be some differences, but that would be probably of the order of perhaps milliamperes, nanoamperes, and I don't know, very small. For the kind of system, perhaps you can kind of guess the amount of the typical amount of the difference that can appear in there. But of course, in most of the situations, we are looking for currents in the DC regime, where we are assuming that the currents are somehow maintained with these constant values. So as a result, these currents are maintained for a long time, which means this delta T can be very long. In that case, even a very tiny difference between these two currents would mean a huge charge pileup in here. So the charge pileups cannot continue. So as a result, in such cases, of course, we will have simply, let me erase everything in here. The rate of change of the amount of the charge within that region would be zero, right? Would be zero, because in DC regime, of course, the amount of the charge in here should not change, which implies that the difference of, these two currents should be the same, right? This implies that this is the case. But of course, just keep in mind that this is an assumption, right? So there are some situations where you can really have different currents at different parts of the same wire. That's a possibility. But there are some certain situations that we meet a lot, in which case that the assumption that the currents are the same is a valid working assumption.